Okay, so as we've been solving some complex polynomials, we've seen that sometimes we get the polynomial down to where we can factor it, and sometimes it's not factorable. So in those cases where it's not factorable, we're going to find that we need a new set of numbers to be able to describe the solutions. So mathematicians created an expanded system of numbers using the imaginary unit defined as, so I is imaginary, and what that means is the square root of -1. And I'm not sure what they want me to fill in here with because I don't know. I'll just say because not all quadratics are factorable. So in order to be able to describe the solutions, we needed something to describe the square root of -1. So if you think about it, I squared, and I'm going to expand that out, I squared equals the square root of -1 times the square root of -1. And so anytime you multiply a square root of something times itself, it brings that number outside of the square root. So to define a couple of things, a complex number, so you'll see it written a lot as a plus bi. And so we say this is the real part and this is the imaginary. Or the real number and the imaginary number. And we'll see later that if we have an imaginary number a plus bi, then its complex conjugate is a minus bi. But we'll get into that. So for a complex number a plus bi, if b equals 0, the number a plus bi equals a is a real number. Yeah, so every number that doesn't have an I component is just a regular real number. If b doesn't equal 0, the number a plus bi is an imaginary number. If a equals 0, the number a plus bi equals, it shouldn't be b, it should be bi. Where b does not equal 0 is called a pure imaginary number. That's where it doesn't have a real component. The set of complex numbers consists of the set of real numbers and the set of imaginary numbers. Okay, so if we're thinking of the set of real numbers, this is the set of reals. Whenever you say with interval notation all the numbers between -infinity and positive infinity, you're in the reals here. And then the reals are divided into rational and irrational. So irrational, so these are all your square roots, your pi, all those never-ending, never-repeating decimals. These are all your decimals and fractions. And then you have your, what's next? Integers. And your whole numbers. And then your natural numbers. Okay, so outside of this set of reals, not part of it, you have the imaginary numbers. Okay, so I want you to picture that real number system is organized in that way, and you've just added a section to your table. So two complex numbers a plus bi and c plus di written in standard form are only equal to each other if, well, the a and the c would have to be equal to each other and the b and the d. So we're going to be doing different operations with the complex numbers. So to add two complex numbers, you are simply going to Oh, how would we describe this? With symbols or words? What do you think? I'm going to say add the real components and add the imaginary. And then for subtraction, we're going to subtract the real part and then subtract the imaginary. Okay, all of this is going to make way more sense when you do examples, but if you can simply remember, the rule is combine like terms. Add real with real and imaginary with imaginary, and you'll be just fine when we go as far as adding and subtracting. The additive identity in the complex number system is so additive identity is whenever you add the opposite to something that it equals 0. So it's the same as in the real number system. This is why I hate fill in the blanks. The additive identity in the complex system is the additive inverse. So I can tell you this: the additive inverse is just the opposite of everything. I could say I plus negative I equals 0, and A plus BI plus negative A plus BI also equals 0. So maybe we'll see some more of that later. So here we have an example. Perform the operations 5 minus 6i minus 3 minus 2i plus 4i. So the first thing I want to do is to distribute that negative sign. So I'm going to rewrite my expression just for funsies. So I have minus 3, and then minus 2i would be plus 2i, and then there's a plus 4i outside the parentheses. So I can combine like terms. So negative 6i plus 2 plus 4, that's positive 6i. So that's an example of the additive inverses. Negative 6 plus 6i is 0. So I'm going to cancel those out. So my final answer is just 2. So to multiply two complex numbers, that is really, if you want to, I'm just going to say use the FOIL method, okay? I think you all know what that means. Whenever you have a binomial times a binomial, you're going to have to use the FOIL method. And so let's go ahead and demonstrate that. I'm just going to show my double distribution here. And I'm going to actually write out every multiplication problem that I'm doing just to be super clear. You guys, if you're comfortable, don't have to do that. So I'm going to do 5 times 3, and I'm going to add that to 5 times negative 2i plus negative 6i times 3 plus negative 6i times negative 2i. So 5 times 3 is 15. This is minus 10i, minus 18i, and then negative 6 times negative 2 is 12, and I times I is negative 1, so that's going to turn that plus 12 that I just got by multiplying two negatives. I'm actually multiplying negative 6 times negative 2 times negative 1. Because negative 1 is what I times I is. And so now I can combine like terms. 15 minus 12 is 3. Negative 10i minus 18i is negative 28i. The product of a pair of complex conjugates is a, let's see, what kind of a number? Well, it's going to end up being a real number because maybe you remember from Algebra 2, whenever you want to get rid of an imaginary or get rid of an I, you can multiply a number times its complex conjugate. To find the quotient of the complex numbers, where C and D are not both 0, you multiply by the conjugate of the denominator. So let's see what that looks like. If I want to divide 1 plus I divided by 2 minus I have always sort of described this. There's a rule that you cannot have an imaginary number in the denominator. It's kind of like you can't have any negative exponents in your final answer. So standard form does not have any imaginaries in the denominator. So to me, that's why you multiply by the conjugate. It just will pull that imaginary out of the denominator. So what is the conjugate of 2 minus I? It's going to be 2 plus I. And we also have a rule in algebra that we're allowed to multiply anything we want any old time by 1, and something divided by itself is equal to 1. So that's why this is legal as well. So I'm going to go ahead and multiply the denominators first, just to show you how that actually gets rid of the real numbers. So, and I'm going to write out my work. 2 times 2 is 4. So negative I times 2 is negative 2I. Positive I times 2 is positive 2I. So I end up with minus 2I plus 2I. And that right there, that's why we do this, because that's the thing that's going to cancel out all of your imaginaries. Then I have minus I times I. So minus I squared, but I squared is negative 1. So I have minus negative 1. So 4 minus minus 1, that's just going to give me a 5 in the denominator. So see, multiplying by the conjugate got rid of the imaginaries. Now I'll go ahead and do my FOIL method on the top. 1 times 2 is 2. 1 times I is I. I times 2 is 2I. I times I is negative 1. So now on the top I get 1 plus 3I. So this is my final answer to that division problem. So here we have a section on complex solutions to quadratic equations. And so now we're going to talk about the quadratic formula. Well, maybe we're not going to talk about it too much. So at the end, your final answer, you might end up with a square root of negative 7, which is not a real number. It's not irrational because it has that negative underneath. And we've always had to restrict the domain and say, oh, well, I guess that means it's no solution. But now, and you've learned this in Algebra 2, by factoring out that I is the square root of negative 1, you can write this number in, and let's see, what vocabulary are we looking for? I don't know what this is called. Maybe in imaginary notation, I'm not really sure. So maybe we'll figure that out. But let's just write that out as I times the square root of 7. So we say that that's a principal square root. So the principal square root of the negative number, negative a, is defined as the square root of a times I. And I always actually put the I in the front. Okay, so that is your crash course on imaginary numbers. Now you are ready to go and practice some imaginary numbers. Thanks for watching.